Hey friends, welcome to the YouTube channel All About Electronics. So in the last video, we have seen that what is Darlington pair and how it can be used as a switch. So in this video, we will see that how it can be used as an amplifier. So this is the circuit of the Darlington amplifier, which acts as a very high performance emitter follower. So as you can see over here the input is applied at the base terminal while the output is taken across the emitter terminal. So we will do both AC and the DC analysis of the given amplifier. And first of all, let us do the DC analysis. So for the DC analysis, these coupling capacitors will act as an open circuit. And if we see the equivalent circuit, then it will look like this. So here, this current is the base current, while this current over here is the collector current, and the current through this emitter resistor is the emitter current. So to find all these currents, first of all let us apply the KVL in this loop. So applying the KVL, we can write voltage VCC minus IB times RB, that is the voltage drop across this resistor RB, minus VBED, that is the voltage drop across the base and the emitter of this Darlington pair, minus IE times RE is equal to 0. So this IE times RE is the voltage drop across this emitter resistor. So here this voltage VBED is the voltage drop across the base and the emitter of this Darlington pair, that is equal to VBE1 plus VBE2. And here this emitter current is equal to beta D times IB, where beta D is approximately equal to beta 1 times beta 2, where beta 1 and the beta 2 are the current gains of this transistor Q1 and the Q2. So from this we can write the first expression as voltage VCC minus IB times RB minus VBED minus beta D times IB times RE, that is equal to 0. Or from this we can say that this base current IB is equal to voltage VCC minus VBED divided by RB plus beta D times RA. So in this way we got the expression of the base current. And here this collector current IC is equal to beta D times IB, because if you are aware, this collector current IC is equal to beta 1 times beta 2 plus beta 1 plus beta 2 times IB, or approximately we can say that it is equal to beta 1 times beta 2 times IB. So in this way we can find the different currents in the Darlington pair. Now commercially, as this Darlington pair is available in a single package, so the value of the beta D is given for the entire pair. But for the academic purpose, if we know the value of this beta 1 and the beta 2, then we can also find the internal collector currents, that is IC1 and the IC2. And from this, we can find the value of the GM1 as well as the GM2. Because this GM1 will be equal to IC1 divided by VT, while this GM2 will be equal to IC2 divided by VT. So in this way, using this DC analysis, we can find the different currents of this Darlington pair, and from this we can also find the value of the transconductance. Alright, so now let's do the AC analysis or the small signal analysis of this Darlington pair. So for the AC analysis, these coupling capacitors will act as a short circuit, while this DC voltage source will act as a 0. And then we can replace this Darlington pair by its small signal model. So this is the small signal model of the Darlington pair. So here, this is the small signal model of the first transistor Q1, while this is the small signal model of the second transistor. And as you can see over here, the collector of both transistors are connected together. Now here, this input as well as this base resistor RB is connected between the base and the ground terminal, while the output is taken across the emitter terminal. So this is the small signal equivalent circuit of this Darlington amplifier. Now because of its very high value of this beta, this Darlington amplifier provides the very high input impedance. So first of all, let us find the input impedance of this Darlington amplifier. And for that, first of all, let us find the equivalent impedance which is seen through the base terminal. Let's call that impedance as the ZB. So here the voltage at this node is equal to VB, and as you can observe, this base voltage VB is equal to the input voltage, and the current to this base terminal is equal to IB. So the ratio of this VB and the IB will give us the base resistance. So to find this base resistance, let us apply the KVL in this loop. Now here this base current IB is equal to IB1. So if we apply the KVL, then we can write this input voltage Vin is equal to voltage Vpi1 plus Vpi2 plus Vout. That is the voltage across the emitter terminal. Now here this Vpi1 is equal to IB1 times Rpi1, while the voltage Vpi2 is equal to IB2 times Rpi2, because here this current is equal to IB2, and this voltage Vout is equal to this IE2 times RE, because here this current is equal to IE2. Now if you observe over here, this current is equal to IE1, and clearly you can see this IB2 is equal to IE1, that is equal to beta 1 plus 1 times IB1, and this emitter current IE2 is equal to beta 2 plus 1 times IB2, which is equal to beta 2 plus 1 times beta 1 plus 1 times IB1. So let us put the value of this IB2 and the IE2 in this expression. That means this input voltage Vin is equal to IB1 times Rpi1 plus beta 1 plus 1 times IB1 times Rpi2 plus beta 1 plus 1 times beta 2 plus 1 times Re. Or we can say that this input voltage is equal to IB1 times Rpi1 plus beta 1 plus 1 times Rpi2 plus beta 1 plus 1 times beta 2 plus 1 times Re. Now as the value of beta 1 and the beta 2 is very high, so approximately we can say that this beta 1 plus 1 is equal to beta 1. Similarly, this beta 2 plus 1 is equal to beta 2, and this input voltage Vin is same as the base voltage. So we can say that the voltage Vb divided by Ib, or the base resistance Zb, is equal to Rpi1 plus beta 1 times Rpi2 plus beta 1 times beta 2 times Re. So this will be the exact expression of the base resistance. But here this first term is much less than the second and the third term. That means here we can neglect this first term. Apart from that, here we can write this Rpi2 as beta 2 divided by Gm. That means we can write this base resistance as beta 1 times beta 2 divided by Gm2 plus beta 1 times beta 2 times Re. And as you are aware, this beta d is approximately equal to beta 1 times beta 2. That means we can say that this base resistance Zb is equal to beta d times 1 over Gm2 plus Re. So if we neglect the first term, then approximately this base resistance can be given by this expression. Now typically, as the value of this beta d is very high, so the base resistance of this Darlington amplifier is also very high. Let's say the value of the beta d is 10,000. And if this term is equal to 100 ohm, then this beta D times this expression will be equal to 10 to the power 6 ohm. Or we can say that it is equal to 1 mega ohm. So as you can see, for this Darlington amplifier, the value of the base resistance is very high. So now we can replace this entire portion which is on the right hand side of this base terminal by the ZB. That means if we see the equivalent circuit, then it will look like this. So now the input impedance which is seen from the input terminal is the parallel combination of this RB and the ZB. That means input impedance is equal to RB parallel ZB, where ZB can be approximately given as beta D times 1 over GM2 plus RE. Now usually when this Darlington pair is used as an amplifier, then this base resistor RB is also very high. And because of that, this input impedance of this Darlington amplifier is also very high. Now similar to the voltage follower, the voltage gain of this amplifier is close to unity. So now let us find out the voltage gain. So the voltage gain is the ratio of the output voltage to the input voltage, right? So here this output voltage is equal to IE2 times RE, that is the voltage drop across this emitter resistor, while the input voltage is the summation of voltage drop across each element. And as we have seen earlier, the input voltage can be given by this expression. That means input voltage Vin is equal to IB1 times RPi1 plus beta 1 plus 1 times RPi2 plus beta 1 plus 1 times beta 2 plus 1 times RE. And as we have seen earlier, approximately it can be given as IB1 times beta D times 1 over GM2 plus RE. Similarly, this emitter current IE2 is equal to beta D times IB1, right? So from this we can say that this voltage gain, that is Vout divided by Vin, is equal to beta D times IB1 times RE divided by beta D times IB1 times 1 divided by GM2 plus RE. Or we can say that this voltage gain is equal to RE divided by 1 over GM2 plus RE. Now typically the value of this 1 over GM2 is much less than the emitter resistor, and because of that the voltage gain of this amplifier is close to unity. So in this way we can also find the voltage gain of this Darlington amplifier. Now if you look this term, then it looks like the voltage divider, right? Because this voltage gain is equal to Vout divided by Vin, which is equal to RE divided by 1 over GM2 plus RE. So based on that, if we draw the equivalent circuit, then it will look like this, where this Rx is approximately equal to 1 over GM2. So this is the equivalent circuit of the amplifier which is seen from the output side. And using this circuit, we can easily find the output impedance of this Darlington amplifier. That means the output impedance is the equivalent impedance which is seen from the output terminal. And to find that, we can consider this input voltage source as 0. So now, if you see over here, these two resistors are connected in the parallel connection. That means output impedance is the parallel combination of this Rx and the Ra. And approximately it is equal to 1 over GM2 in parallel with Re. Now as I said, this 1 over GM2 is much less than the emitter resistor. So approximately we can say that this output impedance is equal to 1 over GM2. So similar to the emitter follower, the voltage gain of this Darlington amplifier is close to unity while the output impedance is very low. But this Darlington amplifier provides the very high input impedance, and at the same time it provides the high current gain. So now for this circuit, let us derive the expression of the AC current gain. So here this current is the input current, while the current which is flowing through this emitter resistor is the output current. So the current gain of this circuit is the ratio of this output current to the input current. Now here this output current is same as the IE2, right? And if you observe over here, this input current gets divided into the two branches. Let's say this current is equal to Ix and this current is the base current. So here to find the current gain, what we will do, first of all, we will find the ratio of this output current to the base current, and then we will find the ratio of the base current to the input current. So in this way, we will find the output current to the input current. So first of all, let us find the ratio of the output current to the base current. Now here, this base current IB1 is same as the IB. That means here IB1 is equal to IB, right? And the output current IO is equal to IE2. Now we know that this output current IO can be given as beta D times IB1, or it is equal to beta 1 plus 1 times beta 2 plus 1 times IB1, right? So we can say that this output current to the base current IB is equal to beta 1 plus 1 times beta 2 plus 1, or it is equal to beta D. So this is the ratio of the output current to the base current. So similarly, now let us find the ratio of the base current to the input current. And to find that, we can replace the entire portion of the circuit which is on the right hand side of this base terminal by its equivalent impedance. And as you are aware, it is nothing but the base impedance. That means if we see the equivalent circuit, then it will look like this. So here, this current is the input current, while this current is the base current. And this base current IB can be found using the current divider rule. That means current IB is equal to RB divided by RB plus ZB times input current. Or we can say that this IB divided by input current is equal to RB divided by RB plus ZB, where ZB is approximately equal to beta D times 1 over Gm2 plus Re. So in this way, we got the ratio of the IB and the input current. So the overall current gain is equal to output current to the base current times base current to the input current. That is equal to beta D times RB divided by RB plus ZB. So this is the expression of the overall current gain. Now as I said earlier, when this Darlington pair is used as an amplifier, then the value of this base resistor RB is higher or comparable to the base resistance. So for a moment, if we assume that this RB is equal to ZB, in that case, this current gain is equal to beta D divided by 2. For example, if beta D is 10,000, then this current gain is still 5,000. So as you can see, this amplifier provides the high current gain. So in this way, this Darlington pair provides very high input impedance and the low output impedance. And if we talk about the voltage and the current gain, then it provides very high current gain and its voltage gain is close to unity. So because of these amplifier characteristics, this Darlington amplifier acts as a very good buffer at the low and the mid frequencies. So I hope in this video you understood how the Darlington pair can be used as an amplifier. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.